Hi, I'm Toby,
I'm Andrew.
and this is our presentation on solar sails.
We're going to start things out by playing a clip for you. In this Star Wars scene, Count Dooku escapes from Geonosis on his King Lorca 116 class interstellar swoop. Once in space, he deploys a solar sail to travel around the galaxy without the trace. Although this technology appears to be common in the Star Wars universe, in our universe, the first spacecrafts relying primarily on solar sails for propulsion were only launched in 2022.
So, what is a solar sail? Well, a solar sail is a spacecraft propelled by sunlight. Whereas conventional rockets are powered by combustion of rocket fuel, a solar sail is pushed forward by the light from the sun. It occurs much like sailboats are propelled on water, where they harness the momentum from wind to travel, except with the momentum from photons from the sun. And current solar sails, as you can see, are made of lightweight materials such as mylar or polyamide coated in a metallic reflective coating.
So, a brief history on the concept of solar sailing. The concept of solar sailing dates back to 400 years ago when German astronomer Johannes Kepler observed comet tails being blown by what he thought was a solar breeze. This idea inspired him to suggest that ships and sails proper for the heavenly air should be fashioned to glide through space. He even wrote to Galileo saying that you should provide ships or sails adapted to the heavenly breezes, and there will be some who brave even that void. And obviously, right here, he wasn't talking exactly about harnessing sunlight. However, he was talking for the first time about harnessing some sort of breeze or energy source in space without using propulsion.
So, for the physics behind solar sails, the physics can be explained using the particle model for light. So light is made up of particles called photons. And photons don't have any mass, but they travel through space, and they do have momentum. And the momentum of a photon can be represented through this equation, h over lambda, where lambda is the wavelength of the photon. This is an example where the lambda is 500 nanometers, which is the average wavelength of a photon in space. So this will come out to be 1.3 times 10 to the negative 27th kilogram meters per second of momentum, which is obviously a minuscule amount. However, since space is a vacuum, meaning it has a zero air resistance, this will build up to be enough to propel it over the time. So when light hits a solar sail, which has a bright mirror-like surface, the photons from that light bounce off the sail like a mirror. And as they hit the sail, their momentum is transferred to it, giving it a small push. And due to the law of conservation of momentum, the change in momentum of a photon must involve equal and opposite change in momentum for the object it interacted with. So, as they bounce off the sail, the photons give it another small push. And both of these pushes are very slight, but since space is vacuum with no air resistance to slow it down, each push allows the vehicle to gain speed.
So when photons transfer momentum to solar sails, the direction of thrust is always perpendicular to the solar sail. So as you can see here, we have a diagram of the mirror, which is the solar sail in this case, and the sun ejecting photons and reflecting against the solar sail. And as you can see, the thrust is perpendicular to the mirror. Now, this same idea persists even when the angle of incidence between photons and the solar sail is at 45 degrees or even 10 degrees. You can see that the thrust is still perpendicular to the solar sail. So this can be displayed by the equation IR, which is the angle of thrust, is equal to thrust times the angle of incidence between photons and the solar sail. This allows solar sails to be able to change the direction of their spacecraft by changing their angle in relation to the sun. The amount of force applied on the sail by photons, however, is greatest when the angle of incidence is 90 degrees. As you can see from this diagram, the percent of perpendicular thrust is 100% when the angle of incidence is 90 degrees, and that percent of perpendicular thrust decreases as the angle of incidence changes or decreases back towards zero. This can be represented by the equation AR, which is the effective area, equals the area of the solar sail in this case, times the angle of incidence between it and the photons of light colliding with it. This represents that effective area, meaning the area that is able to receive the momentum of photons, is determined by the angle of incidence. So if a solar sail is positioned at a certain angle to the sun, the gravity from the sun will apply more force on the spacecraft than photons propelling it. And this is what allows solar sail-powered spacecrafts to be able to travel towards the sun by tacking like a sailboat instead of just traveling away from the sun, being propelled by photons. If the orientation of a sail remains at 90 degrees, for instance, to the direction of the sun, the thrust provided by the sail will cause the spacecraft to steadily lose energy, and the spacecraft will then be able to spiral in towards the sun. This allows solar sails to be able to be used to propel spacecrafts away from the sun to other planets, but also return back towards Earth. Due to the inverse square law, which is intensity is proportional to distance squared, the further away a solar sail is from the sun, the less intensity and corresponding thrust a solar sail spacecraft will receive. Therefore, at distances beyond the orbit of Mars, the sun becomes too faint to push a solar sail, which limits their use deep in space, according to NASA. Ideally, a solar sail is used to travel between short distances between planets. However, because of the tacking system we just showed you, it is able to travel back towards a planet once being propelled away by the sun.
From the Earth, a sail having an area of 100 square meters that is 100% efficient, so in an ideal world, would have a maximum thrust of 0.000908 newtons, which is minuscule compared to the 7.6 million newtons of thrust that a SpaceX Falcon 9 rocket would generate leaving Earth. This illustrates one of the limitations of solar sails. You can't launch them directly from Earth. They have to get into space first. However, due to Isaac Newton's second law of motion, F equals mass times acceleration, over time the speed and the acceleration of the solar sail will increase its velocity to 10,600 kilometers per hour if it's 40 kilograms, without any fuel being used once it's in space.
So NASA recently presented a project in 2020 for solar sails made out of extreme metamaterials, nanostructured, and with some ceramics that will be able to withstand over 1,000 degrees Celsius. They will reach slingshot within 2 to 5 solar radii of the sun, and the solar sail should cost about $10 million, which is relatively cheap or inexpensive for a spacecraft. They will also be able to carry 50 kilograms of payload. It will be 3 times faster than the Voyager probe and could reach Jupiter in 5 months, Neptune in 10 months. This marks the future development of solar sail technology as a way to more quickly and less expensively travel between and explore new planets in the galaxy.
So what solar sails are actually developed today, and how have they been used? So as of now, there are only a few projects that have been successful, but there are some. The first was the Icarus, which was a Japanese aerospace exploration agency experimental aircraft, which was the first to be launched using solar propulsion. It was launched in May 2010 on board a HIIA rocket, and it successfully completed its mission in December of 2010, flying past Venus at around 50,200 miles away out into space, successfully completing its mission, as it was not planning to come back to Earth. And the first successful one to come back to Earth was the LightSail 2 spacecraft, which launched on June 25th, 2019 by the Planetary Society and re-entered Earth's atmosphere on November 17th, 2022, using sunlight alone to change its orbit.
That's right. We'll make a sailor out of you yet.
Thank you for watching.
Thank you very much.
These are our sources.